Respected teacher and all my fellow batchmates, today I, Shandeep Das, a second year student of CGSC, will present my Ca1 on the topic of classification of signals. Before hopping into the topic of classification of signals, we must know what is a signal. A signal is a function that carries information about how a physical quantity changes with respect to one or more independent variables. We can say there are two types of signals. One is continuous time, which depends on continuous variable t. The function depends on the variable t, and discrete time, which the function depends on the discrete variable, wherein is an integer. Some examples of signals are daily temperature readings, voltage in a circuit over time, TV remote control signal, which are infrared light pulses carrying commands, sound from a guitar vibration, pattern of strings, audio waveform of a song. We just discussed there are two types, continuous time and discrete time signals. Uh, a signal is called continuous time when it is defined for every instant of time t in a given range. We can see there is an example where this is dependent on the instant of every instant of time in this range. We can also say that the temperature variation over the day is another example of continuous time because it is on the basis of the entire day, the entire period, every instant of the day. You can see the graph. It is the um, one example of continuous time. Now we come to discrete time signals. A signal is called discrete time dt if it is defined only at a specific discrete time instance. For example, xn is equals to 2, 4, 6, 8. These are specific sample data points. For example, daily temperature recorded at 9 a.m. Only at 9 a.m. means at a specific time when we get the record, when we get the signal, it is called a discrete time. Here is another graph example where n is an integer here. Now we hop into the real topic of my CA1 presentation, classification of signals. There are mainly five types of classification: deterministic and non-deterministic, periodic and non-periodic, symmetric and anti-symmetric, energy signal and power signal, causal and non-causal signal. We will start with the first point, deterministic signals and non-deterministic signals. These deterministic signals are fully described by a mathematical formula. They are predictable at any instant because we can calculate their value with the given formula. Here is an example and here is a graph. Here we can see it is a sine graph. Non-deterministic signals are signals which cannot be predicted exactly. They are basically described statistically by mean, variance, PDF. For example, thermal noise in electronics. We cannot predict this at any given time by any formula. So it is called a non-deterministic signal. Here is a random graph. Non-deterministic signals are also known as random signals. Now, on the second topic, on the second point, periodic signals and aperiodic signals. A signal is periodic if it repeats itself after a fixed interval t called the period. Equation, we can say this is an example xt is equals to xt plus t, where this and this are equal even after t, even after one t period for all t. Where t is the time period, as I said. For discrete time, it is xn is equals to xn plus n, where n is an integer. We know that. Another example, we can see this sine formula. Another example is AC voltage waveform. Here we can see it is repeating after a certain period of time. After t, it is again repeating. Now, aperiodic signals are quite the opposite of periodic signals. It is a signal, we can say a signal is periodic if it does not repeat over time. It is quite obvious. But then also we can see equation xt is not equals to x of t plus t for any fixed t, where t is the time period as we saw here. Another example is t x of t is equals to e to the power minus t. Another example we can see is speech waveform of a conversion ECG signal during irregular heartbeat. Here, these are all irregular. It is not repeating after any other period or time period, a fixed time period T. Now we hop on to the third topic, symmetric signals and anti-symmetric signals. It is also known as even signals, and anti-symmetric signals are also known as odd signals. Even signals. A signal is even if it is symmetric about the vertical axis. We can see xt is the vertical axis, and here it is evenly even. This part, the right hand side of xt and left hand side of xt is the same. Xt is equals to x of minus t for continuous, or x of n is equals to x of minus n for discrete. There are note, we can take a note, mirror image around t is equals to 0 in a graph. Here is an example and here is a graph as I said. Now, anti-symmetric signals, odd signals. A signal is odd if it is anti-symmetric about the vertical axis. We can see that these are these we can see, and anti-symmetric is basically the mirror image of the mirror image. Uh, Here, this mirror image would have been this, but if we place a mirror over here, that would have been like this. So that is known as anti-symmetric. X of t is equals to minus x of minus t, or x of n equals to minus x of minus n. We can take a note, opposite sign on both sides of t is equals to 0. Here is an example, xt of is equals to t, or xt is equals to sin t, and here is a graph. Any signal can be expressed as xt is equals to x e of t plus x naught of minus t, where sorry, x naught of t, there is no minus t, where x of x e of t is equals to half of xt plus x minus t. X naught is of t is equals to half of xt minus x of minus t. We can derive the formula also. Properties of even and odd signals, we should take note. It will be helpful for solving our questions. For even signal, odd signal part is 0. For odd signal, even part is 0. Product of two odd signal is even. Product of two even signal is even. Product of two even and odd. Even into odd is odd. We should take note. Now on to the fourth topic, energy signals versus power signals. A signal is an energy signal if it has finite energy and zero average power. We can take note of the formulas also. Another example is a single pulse of finite duration, Gaussian pulse e to the power minus t of square. Another, this is a degradation graph. We can take note of this also. Now we come to power signals. A signal is a power signal if it has finite non-zero average power and finite energy. We can see there are the formula. This is for continuous time and this is for discrete time. N is the number and T is the time period. This T is the time period. Now note, we can take 0 is lesser than p is lesser than infinite and e equals to infinite. Another example is this sign, where we can see it is an infinite sine wave. Another graph is this graph. Now on to our last topic, or you can say the last point, causal signal and non-causal signal. A signal is causal if it is 0 for all negative time, where t is equals to t is lesser than 0, or in odd, n is lesser than 0. T is lesser than 0 for ct, or n is lesser than 0 for dt. We knew that for a long time. If x of t is equals to 0 for t is lesser than 0, example x of t is equals to e to the power minus t ut. Another example we can see is step signal ut. This is a graph. No zero value for the graph for negative. We can see When we go to the negative side of the graph, there is no signal. So that is called causal signal. And non-causal signal is quite the opposite. A signal is non-causal if it has non-zero values for negative time. T is if t is negative or n is negative. uh, X of t is not equals to 0 for some t negative. T is lesser than 0. That means t is negative. Example, x of t is equals to e to the power minus t for e to the power t for all t. X of t is equals to cos t. Now we can see the graph xt and t. This is the cos graph. We can see for even the negative value there we can find a signal. So it is known as non-causal signal. So that's it from my end. I hope you all understood what I was trying to say by this presentation. Thank you for listening, and here I end my presentation.